All right, let's dive in. Today, we're tackling the ether.
Yeah, this should be fun.
Our listeners specifically requested this one, wanted to understand how this ether thing, well, how it fits into the history of science, I guess.
Right. How it went from like a big deal to, well, not.
Exactly. And we've got a ton of material to help us unpack this papers, summaries, the whole shebang.
Should give us a pretty good picture of how our understanding evolved over time.
So, where do we even begin? I mean, we're talking about a concept that predates modern science.
Okay, so imagine trying to explain the universe, but you don't even have a solid grasp of gravity yet.
Right, like way, way back.
Exactly. That's where the ancient Greeks come in, guys like Aristotle. They came up with this idea of quintessence.
Quintessence. Sounds fancy.
Basically, it was the fifth element. You had earth, air, fire, and water, your basic elements.
Makes sense.
And then you had ether. It was this perfect, unchanging substance, totally different from the messy stuff down here on Earth.
So they were trying to make sense of the heavens, the stars, the planets, all that.
Exactly. They needed something to explain how those celestial objects moved, what they were made of.
And ether was their answer. Like, the heavens are made of this special stuff, totally different from down here.
Yeah. And the funny thing is, this idea stuck around for centuries.
Really?
Those
I mean,
were-
it's not like they had telescopes and labs back then.
Nope. But even big names like Descartes and Newton, they kind of bought into the ether idea too.
Newton, the gravity guy.
The one and only. He had trouble with what he called action at a distance.
Meaning,
Like, how can gravity, a force, act across empty space? It just didn't sit right with him.
yeah, I guess that's kind of weird when you think about it.
So he thought maybe the ether was the answer, a kind of cosmic fluid that filled all of space that gravity could travel through.
So ether was like this invisible glue holding the universe together.
Pretty much. At least that's how they saw it back then.
But then things started to change, right? New discoveries and all that.
Yeah. Fast forward to the 19th century. Electromagnetism was the hot new topic. And then along came James Clerk Maxwell.
Maxwell, wasn't he the guy who figured out that light is an electromagnetic wave?
Yep, that's him. And that discovery, well, it kind of brought the ether back into the spotlight.
How so?
Well, scientists knew that sound waves need air to travel.
Makes sense. I mean, you can't hear anything in a vacuum.
Right. So they figured light waves must need some kind of medium too, something to vibrate in as they travel through space.
Ah, they needed something to carry those light waves. Enter the ether again.
Exactly. They called it the luminiferous ether, the light-carrying ether, and they were determined to prove it existed.
So how'd they go about doing that?
Well, the most famous attempt was the Michelson-Morley experiment in 1887. It was designed to detect what they called the ether wind.
Ether wind.
Imagine the Earth moving through this stationary ether. Like, picture a boat cutting through water.
Okay, I'm picturing it.
So you'd expect this ether wind to affect the speed of light, depending on the direction it's traveling, like a headwind or a tailwind.
Right, so they were trying to measure the speed of light in different directions, expecting to find a difference.
Precisely. But here's the kicker. The experiment showed absolutely no difference.
Wait, so they found nothing?
Zip. Nada. The speed of light remained constant no matter which way they measured it.
Wow. I must have thrown a wrench in the whole ether idea.
You could say that again. This was a major crisis for physics. The experiment that was supposed to prove the ether's existence basically disproved it.
So what happened next? Did they just abandon the ether theory altogether?
Well, it wasn't that simple. There was a lot of head scratching and attempts to explain away the results. But the seed of doubt had been planted. The universe wasn't behaving the way they expected. And it was about to get even weirder thanks to a young guy named Albert Einstein.
Einstein, huh? I have a feeling things are about to get interesting.
Oh, you have no idea.
All right, well, I guess we'll have to save that for part 2 of our deep dive. But before we do, I just want to remind our listener
That the ether's story.
is a reminder that science is all about questioning what we think we know,
Even if it means.
tossing out ideas that have been around for centuries.
Stay curious, folks.
We'll be back soon with more on the ether and its ultimate fate.
So we left off with the ether in a bit of a predicament.
Yeah, that Michelson-Morley experiment really threw a wrench in things.
It did. And this is where Einstein enters the picture. His theory of special relativity, published in 1905, well, it completely changed the game.
I've heard of special relativity. It's all about space and time being relative, right?
That's a part of it. But one of the key postulates, the foundational ideas, is that the speed of light is constant for all observers,
Meaning?
no matter how fast you're moving, even if you're approaching the speed of light. You'll always measure the speed of light to be the same.
That's kind of mind-bending.
It is. But here's the thing. This idea makes the ether completely unnecessary.
How so?
Well, if the speed of light is always constant, it doesn't need a medium to travel through. It's just a fundamental property of the universe.
So no ether wind to detect because there's no ether to begin with.
Exactly. Einstein essentially said, forget the ether. The speed of light is the real constant here.
Old move.
It was revolutionary. And it solved a lot of the problems that the ether theory was facing.
But wait, if there's no ether, how does gravity work? Didn't Newton need the ether to explain how gravity acts across vast distances?
Right, that was a big question. And Einstein had an answer for that too. It came in the form of his theory of general relativity, which he published in 1915.
General relativity. That's the one where gravity is actually the curvature of space-time, right?
You got it. Einstein basically said that gravity isn't a force acting through a medium like the ether, but a warping of the fabric of space-time itself.
Okay, so imagine like a bowling ball on a trampoline.
Perfect analogy. The bowling ball creates a dip in the trampoline, right?
And that's like gravity.
Exactly. Massive objects warp space-time around them, and other objects simply follow the curves.
So no ether needed for gravity either. Einstein really turned things upside down.
He did. And while relativity was a major blow to the ether theory, it wasn't the final nail in the coffin.
There's more.
Oh, yeah. The story of the ether continues with the rise of a completely different branch of physics, quantum mechanics.
Quantum mechanics. Now we're getting into the really weird stuff.
Quantum mechanics and its offspring, quantum field theory, well, they completely revolutionized our understanding of particles and forces.
In what way?
They introduced this idea that everything we see, light, matter, forces, all of it, arises from excitations in fundamental fields.
Fields.
Yeah, these fields permeate all of space. They're the fundamental fabric of reality.
So instead of needing the ether as a medium, these fields themselves become the medium, right?
Precisely. Think of it this way. The electromagnetic field, for instance, isn't something that exists within the ether.
It's something else entirely.
It's a fundamental aspect of space-time itself. And it can ripple and vibrate, creating what we perceive as light and other electromagnetic phenomena.
So no need for the ether to support those waves.
Nope. And this applies to other forces too. The strong force, the weak force, they're all mediated by fields.
What about gravity? Does quantum field theory have an explanation for that as well?
That's the tricky one. We have a really successful quantum field theory for electromagnetism and those other forces I mentioned, but a complete quantum theory of gravity, well, that's still a work in progress.
So there are still some big mysteries out there.
Definitely. But even without a full quantum theory of gravity, quantum field theory paints a very different picture of reality than the one that needed the ether.
Okay, so the ether is pretty much out of the picture at this point, replaced by these fields. But I have to ask about something you mentioned earlier, the quantum vacuum.
Ah, yes, the quantum vacuum.
It sounds kind of spooky. What is it exactly?
Well, it turns out that what we perceive as empty space isn't actually empty at all.
Really? But it looks pretty empty to me.
I know, right?
Yeah.
But according to quantum field theory, even in a perfect vacuum, these fields are constantly fluctuating.
So there's always something going on, even in empty space.
Exactly. It's this dynamic sea of energy with virtual particles popping in and out of existence.
Virtual particles, what are those?
Think of them as temporary fluctuations in the fields. They're like tiny blips of energy that borrow energy from the vacuum, pop into existence for a brief moment, and then disappear.
And this is happening all the time, everywhere.
All the time, everywhere. It's kind of mind-blowing when you think about it. Empty space is anything but empty.
So we went from this static, unchanging ether to a dynamic, bubbling quantum vacuum. Quite a shift in perspective.
It is. And it highlights how our understanding of the universe has evolved over time, becoming more complex and more nuanced.
It's almost like the universe is more interesting without the ether.
I'd say so. But I think the most important takeaway from all of this is that science is a process. It's not about being right or wrong, but about constantly refining our understanding based on new evidence.
So the ether might be gone, but its story teaches us a valuable lesson.
Exactly. And it begs the question, what other scientific ideas that we hold dear today might be overturned in the future?
That's a great question. I guess we'll have to wait and see what the future of science holds. But for now, I think it's time to wrap up this part of our deep dive.
Sounds good to me.
All right, listener, be sure to join us for part 3, where we'll
Explore some of the implications of the ether's demise.
and maybe even speculate about what other scientific revolutions might be on the horizon.
All right, so where were we?
We were talking about how the ether, this once fundamental concept, well, it kind of bit the dust.
Yeah, it's a great example of how science progresses.
Not always in a straight line, more like taking a few detours along the way.
Exactly. Sometimes those detours lead to dead ends, like with the ether,
But other times, they open up whole new avenues of understanding.
like relativity and quantum mechanics.
Exactly. So I'm curious, what other big scientific ideas do you think might experience similar shifts in the future?
Hmm, it's a tough one.
Well, you mentioned dark matter and dark energy last time.
Yeah, those are definitely up there.
Yeah.
We see these gravitational effects in the universe, things we can't explain with the matter we can see.
So we say, okay, there must be something else out there, something we can't detect directly. Let's call it dark matter and dark energy.
Right. And it's possible that, just like the ether, our current ideas about dark matter and dark energy are just placeholders.
For a more complete picture.
Exactly. Maybe we need another Einstein to come along and give us a whole new framework.
Or maybe it'll be someone listening to this right now who cracks the code. But speaking of mysteries, you also mentioned interpretations of quantum mechanics.
Ah, yes, quantum mechanics.
Mm-hmm.
Arguably the most successful theory we have.
But also one of the weirdest.
It makes these incredibly precise predictions about the subatomic world,
Mm.
but it's really hard to wrap your head around what it all means.
Like what's really going on down there?
Right. There are all these different interpretations, each trying to make sense of the weirdness.
Like the Copenhagen interpretation, the many worlds interpretation.
Exactly. But none of them give us a complete picture. It's still an open question.
So we've got these big questions about the nature of reality itself.
And those are the most exciting questions to ask.
For sure. But before we go too far down the philosophical rabbit hole, are there any other areas of science you think might see major shifts in the future?
Well, there's the whole question of the origin of life. How did life arise from non-living matter?
That's a big one. We've got some pretty good ideas, but it's still a mystery.
Right. And it's not just about figuring out how it happened here on Earth. It's also about the possibility of life elsewhere in the universe.
With all those exoplanets we're discovering, it seems more and more likely that we're not alone.
Exactly. And the discovery of extraterrestrial life, even if it's just microbial, would be a game changer.
It would force us to rethink everything we thought we knew about life, the universe, everything.
And who knows, maybe those alien life forms, if they exist, have their own versions of the ether, their own misconceptions about the universe that they'll eventually have to abandon.
That's a really interesting thought. It makes you realize that our current understanding of the universe is just a snapshot in time.
And that's the beauty of science. It's always evolving. It's always pushing the boundaries of what we know.
So, to our listener, I think the biggest takeaway from our deep dive into the ether is this: the universe is full of mysteries, and the journey of discovery is never truly over.
So keep asking questions, keep exploring, and who knows, maybe you'll be the one to make the next big breakthrough.
Thanks for joining us on the deep dive.